So here we are having our chair of the session, Professor Amarnath Hegde. He will be briefly talking about the session and he will introduce us with the speaker. Then we'll proceed with the session. Okay, thank you.
So thank you. So welcome to this parallel session on ground improvement and stabilizations. So basically myself, Dr. Amarnath Hegde, I'm from IIT Dharwad. Actually, I'm the co-chair of this session, but the chair is not around, so I will manage this particular session. So in this session, there are 12 presentations, but hardly, I think, 4 to 5 authors have confirmed as of now. And we have luckily our theme speaker, Dr. Sita Lakshmi is here. So the idea of this particular session is that for theme lecture, we allot 15 minutes, and for normal presentations, there will be 9 minutes of time. So our first, basically, the theme lecture will be delivered by Dr. Sita Lakshmi P. She is from NIT Calicut. She is assistant professor at NIT Calicut. So I try to briefly introduce her before inviting her to deliver this lecture. So she did her PhD from IIT Gandhinagar and postdoctoral from IIT Bombay, and she's an assistant professor at NIT Calicut. Her research interest is mainly into ground improvement and soil stabilization. And she will be speaking today on the topic of enhancing the geotechnical properties of micaceous sand using xanthan gum biopolymer, a sustainable alternative to conventional stabilizers. So with this brief introduction, it's my pleasure to invite Dr. Sita Lakshmi to deliver the theme lecture for 15 minutes. Thank you.
Thank you, sir. Can I talk without mic? Is it okay? Okay. Yeah. So today I'm going to talk on the topic improving the geotechnical characteristics of micaceous sand using different alternative stabilizers. So first of all, due to the rapid demand for... Am I stepping on something? No. Okay. So increasing demand for transportation infrastructure and... This can be switched off. I can talk without. Switch it off. Okay. So it is not coming.
Use the mic because video recording is going on.
Yeah. Okay. Okay. Point. Due to the lack of conventional materials satisfying the IRC codes, we are in need of utilizing many marginal materials. One among them is micaceous sand, which is a soil which contains mica, a mineral, muscovite mineral, which is having platy morphology, which usually occurs in all three types of rocks. This platy morphology comes from the rock formation which has perfect basalt cleavage foliated over each other, so which will have a weaker plane on one side and stronger planes on the other side. That creates a vulnerable mechanism when it is mixed with either clay or sand. So when it is mixed with clay, the cohesive nature of clay predominates, so the mica's vulnerable effect will not be there. But when it is present with sand, so we have this kind of particle arrangements, so which creates non-uniform void spaces all around. When this platy mica particle size is higher than the size of sand particles, then the vulnerability gets increased. So it creates bridging and ordering mechanism, which is essentially creation of this non-uniform void spaces, which basically hinders the sand particles from achieving the closest configuration. So in that case, more non-uniform void space gets created, and it affects basically the densification process, which in turn affects the compressibility, shear strength, and all other geotechnical properties. Okay. Then in addition to that geometrical arrangement, non-uniform void space creation, individual mica particle, if I am considering, which has numerous intact mica flakes which gets overlap each other, and when the load is applied, it tends to bend, flexible enough, and when the load is removed, it tends to rebound and resilient enough to take back its own position. But in that case, it is highly elastic in nature, which we feel may be useful. But these mica particles are having less hardness in the range of 3 in most hard scale compared to that of quartz, which is around 7-8. So when it is mixed with a stronger particle, it tends to crush because of abrasion. So when it is getting crushed, this resilient nature, whatever we feel it is good, may get reduced, and the crushing of particles continuously takes place, which will not give a sustained density or shear strength or compressibility. So which tends to change continuously when the load is applied dynamically, especially in case of traffic loads. If it is static, obviously it will be under compressive load, so there is no rebound nature or crushing. So which may not be vulnerable in the static case, but it is highly vulnerable in case of traffic loading or dynamic loading conditions. That's why in literatures, usually this micaceous sand which has mica more than 10% is usually considered not suitable for pavements, and it is usually taken away and a new good quality material has been replaced. But this study aims to understand what is the basic microscopical mechanism which happens during crushing, and if during crushing, if whatever parameter is getting deteriorated, how can it be regained back using some alternative sustainable stabilizers, not like a cement or lime. Okay, so sorry. So in that case, first we have taken 30% mica and 70% sand, so which is mostly available in the world. Highest percentage of mica ranges from 0 to 70-80%. But basically this mica mineral can be extracted for the electrical industry's purposes because it's a good insulator. But when the percentage of mica is lower than 30%, it is not efficient enough to extract completely. So in that way, up to 30% mica is usually not being extracted. So we have taken 30% mica as the mica percentage in the soil, and it is subjected to basic standard Proctor compaction test to initiate or we increase the percentage of crushing, because we cannot directly simulate the traffic loading to induce the crushing, because that tends to change with the depth and the type of loading, so which makes the process complicated. So just to increase the percentage of crushing, we have increased the number of compaction tests on that. So we have seen that the MDD tends to increase and the OMC tends to decrease, which is a good sign, because when it is in its uncrushed state, it created high non-uniform void spaces because of the bridging and ordering. As the size of the particle decreases, it tends to occupy the pores, so which tends to increase the density. And the particle size indicated that only the larger particles tends to crush faster, while the smaller particles, which was already occupying the pores, was not getting crushed much. So that was obtained from the grain size, which is again absorbed in the SEM images. So initially this intact flakes of mica with smoother surface was absorbed. With increase in degree of crushing, that flakes gets detached along with the crushing from the edges. And the same if we absorb in the X-ray CT analysis, it was observed that in the uncrushed state, the more flaky mica particles tends to occupy a larger space, and it tends to get segregated from the sand particles. So the mica-mica contact was higher, and which was influencing the geotechnical properties in a greater way. But as the percentage of crushing or degree of crushing increased, when the particle size tends to decrease to a very smaller size, and they get occupied internally over the pores, and that becomes uniform also, which is not like segregation of sand and mica particles. So in that way, when the particle size of mica gets to decrease, the detrimental effect of mica is tending to decrease. Further, the permeability analysis showed that the permeability tends to decrease, which is in accordance with the pore size as well. But it was not as considerable as that, because all are in the range of 10 to the power minus 6. So the crushing effect was not much affecting the permeability, because the percentage of mica itself is 30, and among that the larger particles only is getting crushed, so which was not affecting the permeability over a greater extent. And if you see the shear strength parameters, initially the uncrushed one was having 26 angle of friction, while it was increased to almost 33, because the gradual increment in density obviously increases the angle of friction, right? And cyclic CVR test was performed further to check, because the major problem of micaceous soil is under traffic loading, so which was simulated using a cyclic CBR test to understand the resilient modulus parameter variation. It was observed that even though the percentage of crushing increased the shear strength property and permeability or compressibility aspects, the resilient modulus was not getting increased further, only in the range of 35 to 45 only it was ranging. So even though the pores gets occupied, even though the density gets increased, because the sand particles are highly frictional and hard, while the mica particles are still flexible and elastic, weaker. So it is like a weak and strong matrix, which was not improving the resilient modulus. And the CBR also was in the range of 2 to 5% only, not increasing the 5%, which was not satisfying the IRC code. So we went on to increase the geotechnical characteristics of that crushed micaceous sand by addition of xanthangum biopolymer. The percentage increment was done from 0.5, 1 and 1.5 as per the literatures. And it was observed that the strength characteristics was significantly increased with a zero cohesion in micaceous sand, which was purely frictional initially. Addition of xanthangum increased the cohesion characteristics significantly up to 55 to 60 kPa. And the friction angle also increased up to 41 degrees. And with the increase in curing period from 0 days to 7 days, further the cohesion increased from 45 to 133 kPa around, and the friction angle also increased from 36 to 41 around, which can be seen in the failure envelope characteristics. Okay, but so the similar resilient modulus characteristics has been observed, and with the optimum 1% xanthangum biopolymer as stabilizer, the resilient modulus parameter was analyzed using the cyclic CBR testing. In that, we could observe that the CBR for untreated, which was around 2 to 4, which has been significantly increased up to 22 with the xanthangum biopolymer as stabilizer. And accordingly, as the CBR gets increased, accordingly the resilient modulus also linearly correlated with the relation, and the resilient modulus also increased up to 100 MPa. So SCM analysis also stated that it has coated over the mica particles. So this xanthangum biopolymer tends to surface coat the mica particle, which resists that resilient nature, which also further resists the crushing effect. In that case, this is also giving a binding effect in its as compacted state. So that was one observation we have observed. When it is undergoing under a saturated condition, so a durability analysis we have, even though I have not included here, but it was not passing through all 12 wetting drying cycles. This xanthangum, even though it is providing a high strength recognition under as compacted state, but it was not passing through, because that whatever binding action it was providing after curing, which gets crumbled during the durability process. So in that case, this may be provided, this may be suggested as a stabilizing solution only under as compacted condition, which may not be good for saturated conditions, which may be sometimes critical. So then we went on to stabilize it with bentonite as a stabilizer, even though bentonite has its own negative impacts, has expansive nature or shrinking nature. The percentage we have restricted only up to 2, 4 and 6%. We have done even swelling pressure tests and differential free swell index test, which was all well within the permissible limit. So we have gone up to 6% bentonite. I'm sorry. So, and the strength obtained was again as similar to that of xanthan gum stabilization. Not up to the mark, but it is up to 30. There we have obtained cohesion of 40. And the friction angle was increased up to 40, which was similar to that of xanthan gum. And the CBR analysis also we have done. Resilient modulus testing with cyclic CBR testing. In this also we have observed the CBR has been reached up to 15 to 16%, which was not equivalent to that of xanthan gum, but it has given enough strength to satisfy the IRC code requirements of 5% or above or 10% of above CBR to be used it as a subgrade. And resilient modulus also almost 70 to 80 MPa. And when this was subjected to durability analysis, this was passing through all 12 cycles. So this becomes among these two, xanthan gum as well as bentonite, the bentonite percentage of 4% to micaceous sand if we add, which not only provides cohesion to it, but also provides enough binding action. So in that case, again, it also passes through the vulnerable conditions upon wetting and drying. That is, the environmental conditions changes from cooler conditions to wet to dry condition. It was also satisfying very well. So in this case, so we conclude that uncrushed micaceous sand, it has resilient nature. If we restrict the crushing, it itself is behaving better, but that cannot be possible. Because of abrasion, the crushing happens continuously. But when we mix it with xanthan gum, and if we ensure that it is not undergoing that vulnerable saturated condition, still xanthan gum is a better solution. And if we expect this extreme conditions of wetting and drying, bentonite provides a best alternative solution, which not only provides the improved strength, but also helps in diminishing the crushing characteristics of mica. So that is what is our conclusions, and the study is still going on to perform more resilient modulus testing to simulate actual traffic loading conditions, and it is under process. And I acknowledge the work done by my PhD student, Ms. Anjali, which has been presented here, and I also acknowledge ICRB CRG project grant, which is part of this work. Thank you. Thank you for the opportunity.
So thank you, Dr. Seethalakshmi, for excellent presentation. So since we have sufficient time, we can take 1 or 2 questions. If anybody has question, kindly, please, sir, go ahead.
So how is it cost comparative analysis of xanthan on using bentonite? So what will be the economical solution to it?
Economical one is bentonite, sir, because xanthan gum is, because we usually get food grade xanthan gum biopolymer, so that is costly. Bentonite is much cheaper. So industry grade bentonite will be much cheaper. Yeah.
And is there any grade of bentonite that is to be used, because there is a variety of bentonite?
Yes, sir. Actually, we just want the cohesive nature only. So in place of bentonite, if we have highly expansive bentonite, that is also still vulnerable. Okay. So moderately expansive bentonite would be better. Here the mechanism is like that resilient nature and the expansive nature gets counteractive. So if the expansive nature gets higher than this resilient nature, then also it becomes a problem. So in that way, it should be moderately expansive. Otherwise, that should not be a problem. The stabilizer itself should not become as a problem. Yeah. Yes.
And what will be the process of mixing, like?
Because bentonite has that expansive nature. So whatever water content which is equivalent to that of optimum moisture content from the compaction test we have taken, with that water, this weighted average percentage of bentonite has been mixed, and thoroughly it is made as a slurry, and that was kept aside for 5 to 6 hours to get it under a stable equilibrium. Okay. Then further it has been mixed with the oven dried micaceous sand. So basically the slurry has to be mixed with the micaceous sand.
Thank you.
Actually, I'm not aware about mineralogy of micaceous soil. You showed something on first slide or
Yes,
second
yes,
slide.
yes, yes.
Is it very similar to our bentonite or something?
Yes,
One level?
it is illite and biotite. Yeah, all are in the same clay mineralogy.
Okay, same
Yes, yes,
family.
yes,
Okay.
yes.
Other thing is like means whether you do with the XG or whether you do with this one bentonite, means if it is not satisfying this betting drying cycles, means what
Bentonite is
can
satisfying actually.
it is satisfying?
Yes,
It
xanthan
is
gum
not
was not
getting
satisfying.
crumbled.
No,
Okay.
bentonite, addition of bentonite was satisfying the wetting drying cycles.
Okay. How much percentage you added?
This optimum we have taken up to 6% also strength is increasing,
Okay,
but we
only
have
up to
taken
6%.
optimum as
Fine.
4%.
Okay, okay.
Yeah.
What was the properties of bentonite? Liquid limit or anything?
That I have not included, but it was less than 100 because moderately expansive it should be.
Okay.
It should not be highly expansive, otherwise that itself
And
become a problem.
apart from this one, XG you said like
Yes,
good
xanthan
good option or something, but we are having the problem of the degradation. Any
Yes,
study?
until unless it is not getting fully saturated. When it is getting saturated, that binding action gets crumbled instantly. So if we maintain, if we make sure it is not getting, if the soil is not reaching to that critical saturated condition, if it is as compacted condition, let's say semi-arid region where rainfall is not occurring frequently, so it may not be going that wetting cycle continuously, right?
Fine.
So in that case, it would be better.
So thank you for the excellent presentation, Dr. Sita Lakshmi. So we thank the speaker with big hands. Please. Now it's time to start with our contributory presentations. So there are only 4 presenters are around out of 11. So we can take sufficiently, 9 to 10 minutes each of you. And the first presenter today who is available is Mohammad Nuruddin, who is basically presenting the paper Compressibility and Shrinkage Characteristics of Clayey Soil Amended with Sugarcane Bagasse Biochar. Yeah, you can take around 10 minutes time.
I can. Sir, shall I start, sir? Good afternoon to all. This is Mohammad Nuruddin, as a research scholar in Civil Engineering Department at National Institute of Technology, Warangal. I am presenting my work on compressibility and shrinkage characteristics of clayey soils amended with sugarcane bagasse biochar under the guidance of Dr. Arif. So my presentation goes this way, starts with introduction, objectives followed by materials and methodology, results and discussions, and finally the conclusions. Basically, the presence of loose pockets and voids in clayey soils can directly leads to the drastic settlements in the soils, and which leads in turn affect the stability of the soil. Thereby, it affects the constructed buildings, embankments, foundations, etc., which have been constructed on these problematic soils. So the main disadvantage constructing on problematic soils is it can leads to cracks, settlements in buildings, failures in landfill liners, then pavements. So many researchers have been using conventional admixtures like lime, cement to mitigate this problem. However, this is not a sustainable material, and also it has carbon intensive disadvantages. So there is a need to bring a sustainable material. So in this regard, we have used biochar to mitigate this problem. Basically, biochar is a rich carbonaceous material which is produced from the pyrolysis of feedstock. And to produce this, we have to vary the temperature at different time periods. And with production of biochar, we are using this biochar because of its effective properties like cation exchange capacity, and it also retains more water, also nutrients. Then this has shown its efficiency as a good adsorbent in polluted soils to mitigate the transmission of heavy metals. And also it has high porosity and it leads to the great surface specific surface area. And finally, because of its numerous surface functional groups on the surface of the biochar helps in mitigating the heavy metals. However, this material has been explored in the area of geoenvironmental engineering, but it has not been efficiently explored in reducing the compressibility and shrinkage characteristics of clay soils. So here we have investigated the compressibility, permeability, and also the shrinkage properties of clay soils using this sugarcane bagasse biochar. So in this study, we have determined void ratios, compression index, coefficient of consolidation, and also the permeability. So coming to the material, as I also already told, we have used sugarcane bagasse. After sun drying this sugarcane bagasse, we have kept this in oxygen limited containers and we have heated it in muffle furnace at 400 degrees Celsius for 40 minutes. Then this figure shows the produced biochar. So from here we have grinded it and sieved through 75 microns to achieve fine biochar. Anyhow, during the process, there are many factors playing to produce the biochar, such as temperature rate, and also the duration. So, at varying temperatures from 250 degrees Celsius to 500 degrees Celsius, by maintaining a constant time for 40 minutes, we have analyzed the yield and elemental compositions of biochar. Here, the maximum yield was achieved at 350 degrees Celsius, that is 25%. Then, but the quality can be determined based on the carbon content it has. The highest carbon content of 60% was achieved at 500 degrees Celsius. So, as an optimal temperature, we have considered 400 degrees Celsius, which has around 23.67% yield, as well as around 60% of carbon in it. These are the basic properties of the untreated soils we have taken. We can see the liquid limit, which is around 65%. We can consider this more problematic due to its high plasticity index. Sorry. So this figure shows, this is the actual microstructural image of the bamboo biochar we have studied. So here we can see more pores on the surface of this biochar. And these are the elemental composition of the biochar. So from one-dimensional consolidation test, we have determined the void ratios. This black line shows the untreated soil, which has the highest void ratio of 0.6, around 0.6. But after treating with sugarcane bagasse biochar at different dosages from 3% to 12%, the highest, the more reduction was observed in 9%. That is around 0.44. This is the initial void ratio. So this the attribution of this reduction from 0.6 to 0.44 can be due to the rearrangement of biochar particles in the pore voids of the soil. Then this figure shows the compression index. Here this black line is the compression index variation with consolidation pressure for untreated soil. This is very clear that with increasing consolidation pressure, the compression index reduced gradually. However, the abrupt changes, more fluctuations are observed in biochar treated samples. But here we can observe for 6, 9, and 12% dosages, there is a similar trend with an increase in compression index up to 400 pressure. Thereafter, there is a reduction at 800 kPa. But in 3% as sugarcane bagasse biochar treated sample, after 400 kPa, the more increase is observed. That can be, we have investigated it through SEM images, SEM analysis. So here the images shows of fragmentation of biochar particles have occurred. That means the biochar particles were crushed during this high pressure. So due to which the more compression index was observed at 800 kPa. Then the coefficient of permeability was also determined with increasing biochar dosage. The permeability coefficient was reduced, and it was around reduced to around 3.3 into 10 power minus 8 centimeter per second. But after that, the more increase was observed at 12% dosages. That was attributed due to the formation of cracks around the biochar particles after getting dried. So this is the reason for increase in permeability at higher dosages. So this mechanism figure shows you at lower dosages, the more voids were occupied by the biochar particles. But at high dosages, increased biochar particles created more voids. Thereafter, at a dried condition, cracks were formed. So here, which are evident in the SEM images. Due to this, the permeability was increased. So to check, to confirm it, we have conducted linear shrinkage test. So the figure 7 shows the binary image generated with ImageJ software shows a crack in the sample. This is the untreated sample, but we have done for the different biochar dosages. But here for timing, I have mentioned 9% dosage, which is the optimal dosage observed in the previous slides. So this image shows there were no cracks observed in the 9% dosage. So from this, we can conclude this 9% dosage can be considered as an optimal dosage, which can help in reducing the compressibility and as well as shrinkage cracks. But in compression index, there are many variations observed with varying consolidation pressures. Sorry. So only 3% biochar treated samples have shown increased compression index at higher dosages. But at 6, 9 and 12 dosages, a reduced compression was observed even at higher consolidation pressures. So these are the references I have gone through. Thank you.
So thank you, Mr. Nuruddin. Any questions for him? Please.
Nice presentation.
Thank you.
You talk about functional groups. Can you please let us know like what kind of functional groups are present?
Yeah, we have done FTR analysis to determine the functional groups which are present on the surface of the biochar. We observed oxygen contained and hydroxyl functional groups on the biochar surface.
So what is the role of those functional groups?
Here actually in this study we have tried to correlate the FTR data with the observed results, but it have not involved in the chemical reactions in the process. So the main mechanism for this reduction is only by the physically rearrangement of the biochar particles.
Okay, basically you are just determining the characteristic of biochar.
Yeah.
Okay, fine. And how you are maintaining, like how you are doing this stability? Like you are mixing the biochar with the clay samples.
Yeah, directly we are adding dry biochar in dried clay samples.
Okay, and in one of your slide you mentioned that while preparing the biochar you maintain the anaerobic condition.
Yeah, during the production of
Is there
biochar.
any production of microbes or some kind of?
This is just an inert material. No microbes are.
Nothing?
No, nothing.
Okay, fine. You mentioned the highest range of temperature is around 500 degrees
Yeah,
Celsius and
yes.
it was having the higher content of calcium.
Yeah.
Oh, carbon.
Carbon, it's
Sorry,
carbon.
Sorry.
Yeah.
Carbon. So if we go beyond the 500 degrees Celsius, we might get more amount of carbon.
Obviously, we get.
Then why you are not going to higher temperature?
If I go beyond 500, I cannot justify with the highest temperature, which can lead to, which cannot be an economical way to produce the biochar. Even at 800, 900 degrees Celsius, we are getting more carbon content in it. But if we, as per the literature, getting more than 50% carbon in it is sufficient.
Okay, fine. And in one of your SAM slide, you showed that bamboo microstructure.
Yes.
So you are using bamboo or sugarcane?
Sorry, it's sugarcane. I'm sorry.
Okay.
It's sugarcane.
In your
Yeah.
one of your slide, you said.
Oh,
Okay.
because I am working on both the materials, just confused.
Okay.
But
Fine.
for here, I am just focusing on sugarcane bagasse biochar. Yeah.
Okay, fine. Thank you.
Yeah.
Any more question from anybody?
What is the particle size of biochar?
We have grounded and sieved through 75 microns. 75 microns.
Okay. Do you think the particle size will have some effect on that compressibility behavior?
Yeah, obviously it will. Because here I have only mentioned fine biochar particles, but we have done it for coarse biochar also. The size was around passing 1.18 mm. So with that, we have seen more compression observed in biochar treated samples. So I have shown you the same image. So these are the crushed biochar particles. In coarse biochar particles, more crushing was observed because the particle size was more. So the affinity of getting crushed was high.
Even at lower consolidation?
Even at
pressures?
lower, yes, ma'am. Here we have observed it at 800, but there we have observed at 400 kP only because of its particle size. So particle size also plays a major role.
One last question, please.
Yeah. Actually, you showed some hydraulic conductivity data. So you have done it with the falling head, or you?
We have
dragged
done in
it from
1D consolidation test.
one day? But that is not the
but,
correct means that has certain limitations.
Yeah.
You must be knowing.
We have already
Like,
tried it, but
because your CV, you could have tried for like.
we have already tried, but it's not working. It is not giving water coming out of it. It's more impermeable that we have waited for almost 6 months, but have not seen even a single drop coming out of it.
Okay.
Yeah, that's why I have calculated with MV and CV values, a correlated equation.
Okay, so thank you, Mr.
Yeah, thank you.
Nuruddin, for a very good presentation. So the next presenter is Mr. Manohar Hussain. So he basically presenting on stabilization of clay soil with GGBS based hybrid alkali activated cement.
Good afternoon to all, respected sir and my dear friends. I am going to present stabilization of clay soil using GGBS-based hybrid alkali activated cement. And one of my students, Sanwar Arafat, is the author and myself is the co-author. So we know that clay is characterized as a low strength and high compressibility, and there is a secondary consolidation, that is your creep deformations and low permeability. So causes destruction damage in the civil engineering structure, like in a road, excessive setting, excessive rutting, like that is a excessive settlement, and due to that there is a damage in the road. And classical problems, we know that there is a tilting of this differential settlement which occurred in the Leaning Tower of Pisa. And other problems in our Silchar regions, NIT Silchar region in Assam, and there is a newly constructed national highway in 39, and which is passes through the soft soil or is some part of the organic soil. So due to that, there is a damage, that means a punching failures occurs in the embankment, So it was found that there is a subsoil and or some part of organic soil is there. Due to that load, there is a the subsoil is squeezing in from that soil, causes nearby this site is heaving and shrinkage problem. That is the problem in the clay soil. So that's why different researchers are reported chemical stabilizations. There is a number of ground improvement techniques. So out of that, chemical stabilization is one of the best solutions, best performance. So chemical stabilization generally popular use traditional materials and non-traditional materials. Traditional materials like lime cements are used because there is binding materials. Due to that cementitious material form, calcium silicate hydride, calcium aluminum hydride, which is binding the soil particles. But there, in this method, traditional method, there is a problem is durability problems and environmental problems. That's why people think in some waste material, non-traditional materials can be used as a research material like geopolymers and hybrid geopolymers. So in this method, in geopolymers, generally is a waste materials which is a amorphous material like GGBS, fly ash, or that are generally used. That is called the aluminum silicate materials. Is activated through a alkali activated, either in a sodium hydroxide or a potassium hydroxide is activated, which is from the geopolymer monomers. This geopolymer monomers is again finally it will form as a silica oxygen chain or a oxygen aluminum chain, which is a polymeric chain. And basically it will form in a sodium aluminum silicate hydrate or sometimes calcium silicate hydrate. So there is a number of stages. Finally, it will get at the polymeric station, which that the geopolymers, the polymeric material like a sodium silicate hydrate is binding the soil particles, and the main soil as a filler material, the waste material is activated, which release the calciums and silica that are form the geopolymeric materials, and which materials is binding the whole the soil, and due to the setting and hardening, then it will make as a very hard and a smooth surface. But in this method, there is some problem. That is your potential is alkali to silica reactions is problem. All materials we cannot form the geopolymerize. It should be amorphous. Silica by alumina ratio should be 2 to 4. There is some conditions. And high shrinkage problem. There is to first setting, very first setting, and affluences occur. And sometimes it's required heat curing. So this problem we can solve by using some new binder materials, that is called a HAC, that is a hybrid alkali activated cement. In this hybrid alkali activated cement, soil is mixed with some SCMs, that means supplementary cemented materials like waste materials, and some amount of OPC is used. That means it is ordinary Portland cement, and then it is activated. Then it is called a hybrid alkali activated cement. So, in this process, already have told, the high amount of, generally greater than 70% amount of waste material is replaces as with use with some binder is your Portland, ordinary Portland cement, and then it will activated and mixed thoroughly, and then it will form the hybrid alkali activated cement. So, hybrid alkali activated cement is a very complex because when you add this aluminum silicate means here we use GGBS, and because in the GGBS silica and aluminum both are there, and then OPC is calcium and silicate is there. So when you alkali activated, then it will dissolutions, and finally it will be products, is cementitious product, really high and high strength it will give, that is sodium calcium aluminum silicate hydrate gel and calcium aluminum silicate hydrate gel is formed, which are the main products which govern the strength performance of a stabilized soil. So in this study we have objective, there is two objectives. One is you are to stabilize the clay soil using GGBS based hybrid alkali activated cement, and then it will finally we'll see the microstructural behavior through different tests. So the scopes is that there to check the performance and of the stabilized soil. We use the unconfined compressive strength test, and chemically sense we have used the pH and electrical conductivity, and then finally we study through the XRD and SEM test. Then soil is collected from this year. This is India, Assam. The northeast part is the corner part. That is your Kasar district. From this Kasar district, here in this part, national highway, there is 39. The soil is collected from there, and then is characterized in the laboratory. It is found that clay with a high compressibility, which have a high amount of clay content. Then, and we use some GGBS, granulated blast furnace slash. So in this part, GGBS is calcium is there, high amount, silica is there, alumina oxide is there. So to form the geopolymer, so silica and oxygen, silica and alumina is important. So their ratio should be maintained. It should be 2 to 4. So there, silica by alumina is amorphous crystalline materials, and for silica to alumina ratio, it is 2 to 4. Is to get 2.5. We have received. Then this is the pictures, and then we use the commercially available OPC 53 cement and sodium hydroxide pellets are used.
Professor Hussain, you have 2 more minutes.
Okay,
Yeah,
we finish.
kindly.
And then we prepared the UCS, first mixed the soil and cement, all this one, and then activated, then prepared the unconfined compressive strength test. Then we see a number of combinations we have prepared and replaced the GGBS with number of percentage like 0, 10, 20, 30, 40%, and a different amount of A by B ratio, alkali to binder ratio, sodium hydroxide at molarity content, and different curing period. And then we find that to prepare to form the geopolymer, you should have here, it should be pH value 10.5. So at a 3%, 3 molarity, it is not formed. That means it is not dissolutions, the silica and alumina. And the 6 and 9, the pH value is greater than 10. That means it will form geopolymer. So that's why, so at 9% molarity, it showed a high strength. So we have 2 parts. One is your geopolymer, another is your geopolymeric, what is called the HAC. So in this, when it will HAC materials, that means hybrid alkali activated, so strength is improved 350 times compared to the untreated soil, and 20 times compared to the geopolymer stabilized soil. And for curing further improve the your geopolymer soil. Also, it is the factors. The strength is the factors. It is depends on the various factors like OPC, a replacement, then curing period, then A by B ratio. All these are studied. And finally, from this microstructure, untreated soil has there is some pores and some flaky structure. But cement treated, that means cementitious compounds are formed when it will HAC treated, and a smooth surface, very hard structure it will form. That's why strength is improved. And finally, then again we studied through the mineralogically from XRD, we found that for a HAC treated, it will form the calcium aluminum silicate hydrate, which is the main materials to form the improve the strength. So from these combinations, we get that 9 molarity at 0.7 A by B binder ratio, and 80% of out of 20% of binder, that is your 80% GGBS and 20% OPC, it will give the optimum value. So all factors, it is depends on number of factors. Out of that is your alkali activators, A by B ratio, curing period, UCS is improved. And then that improvement already I've told is improved is 7.5 MPa, that is 7,500 kPa, that is nothing but 350 times improved and 20 times the geopolymer. And pH value improve the molarity. Molarity, if it is molarity improve, pH improve. pH improve, that means your more dissolutions, more cementitious material form, that will confirm from this XRD and SCM test. Okay, thank you.
Yeah, thank you, Professor Hussain. Any quick questions? 1 or 2 questions quickly. So if no questions, thank you very much for the good presentation. So now I invite Ms. Vandana Brar to present paper on experimental evaluation of electrodeposits in silica sand under varying humidity controlled environment. So you have 9 minutes.
Okay. So a very good afternoon to all of you. I am Vandana Barar, a PhD student from Department of Civil and Environmental Engineering at IIT Delhi. Today I will be presenting my work on the durability of electric field induced electrodeposits in silica sand under different humidity conditions. So, due to ground instability, lot of natural and anthropogenic hazards takes place, like coastal erosion, landslide, liquefaction, and subsidence due to the underground tunneling constructions. So, there are lot of methods which are used to mitigate these problems, such as grouting, deep mixing, and the use of geosynthetics. However, these methods are expensive, prolonged, and destructive in nature, and these methods are effective only for few years and may cause ecological barriers. So to address this associated challenge with the traditional methods, a new innovative approach of electrodeposition can be used. So basically, here I am considering the granular material, basically a sand. So if we are applying electric field in the presence of some chemical solution to the sand, it will introduce some solidified compound in the pore space of the sand, which increases its shear strength and reduce its permeability, so that we can mitigate the hazards like landslide, liquefaction, and subsidence. So, however, there is no study on the durability of these electrodeposits under humid conditions. So, here I will explain you like what electrodeposition is, how it will take place. So, basically, if we are considering the granular material, it was having a lot of pore space. Then we add some amount of water in it to fully saturate the soil, and we install 2 electrodes, anode and cathode, across the soil sample. Then we apply the electric field to the sand, which lead to the formation of, which lead to the electrolysis and electromigration of cation and anion. Due to this movement, these chemical and cation and anion react with each other to form the solid compounds inside the pore space of sand, which reduce the permeability and increase its shear strength. So for the present study, I did testing on this custom made cell. Here I did the same method as I explained earlier. Here I used silica sand as a tested material and used calcium chloride and sodium metasilicate. Then I used carbon felt as a electrode material, as it is cheap in, and then I applied 2.5 voltage per centimeter of voltage gradient, and after the 6 hours of duration, we are able to get a solidified sample. Then I place this sample in a humid condition for 72 hours at 95% humidity conditions. So what is happening inside the sample? So here I'll explain you the basic chemistry. Like I used calcium chloride solution at the anodic side and sodium metasilicates at the cathodic side. Both of these chemical solution get ionized when we apply the electric field, and these chemicals react with each other to form calcium silicate hydrate and sodium chloride. So to further analyze the microstructural behavior of this treated silica sand sample under the humid condition, I did SAM on these samples. First one shows the intact structure, like without the humid condition. You can see that how the granular sand is behaving, like it is retaining its strength. But after the humid exposure, it completely collapsed, and from the SAM images you can see that lot of electrodeposits get leached out. For the further analysis of mechanical behavior, I performed penetration resistance test using the Wickett apparatus. In this apparatus, I put my sample below the needle, then I allow the needle to penetrate into the sample, which gave me the stiffness. So at 0% humidity, I am able to get the higher penetration resistance of 2.5 centimeter inverse. However, after the humid conditions, the penetration resistance lower down by the 2.5 centimeter inverse. So this is because of the leaching of CSH gel out of the silica sand pore space, which critically reduce the stiffness of the treated silica sand samples. So at the end, I would like to conclude this. First, we converted the granular soil to the soft rock. Then after that, there's some issue. Okay. Fine. Okay. Fine. So after converting the granular material to the soft rock, I expose this sample to the humidity condition. Then we get the complete collapse sample. So basically, in this study, we need to explore more wetting fluid so that we can get the sample with that can sustain its strength under the humid conditions also. So currently, I am working on the same. Thank you.
Question? So I have one quick question.
Yes, sir.
Your penetration rate was less at the higher humidity levels, right?
Yes, sir.
So what was the reason for that?
Because my whole sample got disintegrated. Like you can see here, at the 95% humidity, you can see like there is no stiffness in this sample.
Okay.
So that's why we are getting the lowest
All right.
penetration.
Okay, it got collapsed.
Yes, sir.
Okay. And any more question from any audience?
Yes, ma'am.
Please.
So you have done that process of creating the gel formation, right? Deposit,
Yes, sir.
electrodeposits. After that, if we take it under curing and then subject to this humidity, will
Yes,
it have
I am
some
doing
effect?
the study on the same. Like if we cure the sample at the lower temperature, basically I also did some temperature studies that I'm not presenting here. So at lower temperature, we can maintain its strength. Like if after preparing the sample, then we place it in lower temperature ranges, then we can maintain its strength. Like if we are putting the sample at 8 degrees Celsius temperature for 72 hours, and then we are placing that sample in the humidifiers, then we are able to maintain the strength.
Okay, so basically that this hydration process which happens in chemically stabilized soil, right? So the same thing can happen here also,
Yeah,
right?
it's somewhat similar to cement.
So
Yeah.
that is what I'm saying. If the same sample under conventional curing 7 days, 14 days, if I'm doing,
Yes, sir.
and further if we do this process,
Then we
subjected
can-
to relative humidity,
Yes,
then
ma'am.
the process will be completely different.
Yes, ma'am.
Okay, so thank you for
you,
the
sir.
excellent presentation. So, yeah. Now I invite Mr. Himanshu Yadav to present his paper on role of natural moisture in geopolymerization process of marine clay improvement.
Good afternoon, everyone. I am Dr. Himanshu Yadav, postdoc fellow at IIT Bombay. This work has been done with under the guidance of Professor Dasaka Murthy and Professor Hari Prasad Reddy from NIT Warangal. So here is the outline of my presentation. Initially, I will introduce you with the topic, then we'll go with materials methodology, then I will discuss about the results. So moving on to the basically what happens when we go to the field for any pavement, subgrade construction or something, then it's sometimes very difficult due to the weak strata of marine clay or some soft soil that we get there, which lead to the such kind of failures in the field due to the low shear strength of the material. So other thing is we have naturally certain moisture content in the field. So whenever we apply certain chemical stabilizers in the field, the natural moisture content is not taken into account generally. So in this particular study for geopolymerization process, I took into account the natural moisture content present inside the soil. So geopolymerization process is nothing but basically dissolution of aluminosilicates from clay minerals into individual particles. Then in further steps, it will be coming like a 3D network structure for this particular gel. So moving on to the materials, this marine clay was obtained from Mumbai only, and we conducted the liquid limit in slurry state after 4 days, and we got the liquid limit around 83% for this particular marine clay, and sodium hydroxide and sodium silicate solutions were utilized in this particular work. So natural moisture content, if I talk about, when we collected the samples, it was around 11% for this particular marine clay. Then we did the first compaction on the same soil. This standard Proctor test we conducted, and after that we kept 1/3 of OMC, we kept water, and other 2/3 of OMC we added. Behind this particular logic, we were like, if we amend it with the alkali in the field, then what will happen in the situation? That's why we consider 1/3 of OMC that is already present in the field, and 2/3 we additionally add. So that impact we wanted to see. So on the same, whatever OMC MDD we got, that for that OMC MDD, we conducted the strength test. So here are the results for the compaction test. So for compaction, this maximum dry unit weight and optimum liquid content for this particular clay was changing. If I talk about the pattern, this liquid content was decreasing with increase in the concentrations of NaOH and sodium silicate, and density, dry unit weight density for this particular clay was increasing. So here is the stress strain curve for all of those materials, improved materials with different curing periods. You can see within first day or something, almost every clay was showing same results. However, with time it got improved, and in last sample it showed significant strength as compared to other one. So if we talk about the process, like one thing is the change in this particular marine clay, alone marine clay, whatever has been compacted water, there some strength change was observed. That strength change is due to the suction changes, and apart from that, we also observed lower strength, reduction in strength, as we can see in 1 day. In first sample, that reduction is due to the breaking of this our aluminosilicate structure into individual aluminosilicate particles, alumina and silicate particles, and the formation of geopolymerization process was slightly slower. That's why it took time to attain certain particular strength. And other thing I would like to emphasize, the highest strength was observed for the combination of NaOH and silicate. Here NaOH and silicate both are having different roles. NaOH is kind of acting as an activator and making these alumina and silicate particles into separate units. However, silicate is acting as a binding unit and trying to bind these particular things and accelerate it. And when we get combination of both the things, that performed well in this particular case for this particular marine clay. So moving on to the conclusions, this particular maximum dry unit weight of marine clay increases and oil optimum liquid content decreases with increase in alkali content. And similarly, this particular improvement is highly dependent on curing period. So it was like for 7 days we got maximum improvement, and a combination of both sodium hydroxide and sodium silicate was maximum, that was better. And also formation of Nash gel and 3D complex was able to improve our marine clay soil. So these are references. Thank you.
Yeah, thank you, Dr. Yadav.
Okay, thank you, sir.
Any question? Yeah, please go ahead.
I just want to ask, the curing was for 7 days, right? The maximum curing period?
Actually, I conducted for 28 days also, but here I showed up to 7 days only. Means later I conducted,
So what was the curing condition? Was it in ambient condition? Or?
ambient condition. Every experiment has been conducted in ambient, because we will not be getting 60 degrees Celsius. I know, like if we heat the sample, we will getting the more strength. But what is the point of doing that? Because we will never get 60 degrees Celsius or something in the field for our soils. That's why I kept in ambient condition only.
So beyond 28 days, it was not done?
Beyond?
Yes.
20,
28 days.
up to 28 days I have done. Yeah.
So
Those results was almost similar to whatever I showed for 7 days.
okay.
Not significant change from that.
Okay. Thank you.
Thank you.
No, I have not used any waste. Actually, role of natural moistures I was just about to see. Means only natural marine clay was used in this particular work. Sodium hydroxide and sodium silicate. Yeah.
Have you checked what are the oxide contents are there in the sample?
Oxide contents, no. For this particular marine clay, I didn't check. Yeah.
Actually, to form the geopolymer, silica by alumina ratio is
That is important. I
So
understood.
oxide
I
part
can
is
understand.
very important. results.
That is
And
an.
metacalins are used. So I don't know in mineral clay there is a alumina or silica is there.
No, it's
Or
there.
is
It's there.
But
It's there.
ratio it will maintain or not. So please check it. And it is not depend only the molarity. It is dependent on alkali by binder ratio, and also molarity is also important. Important how it is varies. That part is also there.
Okay, sir.
Okay. And then compaction is very difficult because it is a very
And
stiff.
for everything.
So people generally recommended for to compact at a liquid limit.
No, actually, generally that will change whole scenario. So that's why we conducted on every sample.
Your compaction results it is not reflect because you have shown in graphs different molarities and different conditions. Actually, it should be uniform. Molarity should be uniform.
No, like
Conditions
if we
should be
will,
uniform. Then
if
you can differentiate your how it will affect in MDD and worms.
if we will be changing the pore fluids, the conditions will be changing. That's why I considered like doing compaction on the same pore fluid, because pore fluid definitely changes arrangement.
Please study the XRD.
Sorry?
XRD. What are the minerals forms? Then you can understand that there is a geopolymer.
I have studied,
Only just for
but not showed here in this particular presentation. I have studied the mineralogical compositions and the formation of these particular minerals also.
Last one more.
Yeah.
Actually, to form a geopolymer, it needs amorphous aluminum silicate material.
Yeah.
So marine clay is not a amorphous aluminum silicate material.
That's
It
why-
is a crystal material. So I think it is not a geopolymerase. Some sodium hydroxide treated soil. So please.
So what happens? This one, that's why it showed less strength. What means some cases it showed less strength. It doesn't showed. So whatever you said, huh?
It is not a form geopolymerase. It is a stabilizer of sodium hydroxide soil. If you do the sodium hydroxide,
Okay.
is a alkali activated, then it will clay is improve the strength.
Mhm.
At
I
high
can-
alkali, they dissolve the aluminum silica. So maybe not a geopolymerase.
Okay.
Okay, because it is not a crystal material. So to form the geopolymer, it should be amorphous aluminum silicate material. One condition.
So-
And second condition, silica by aluminum ratio should be 2 to 4.
2 to 4. That I checked. Yeah, it was 2 to 4.
Yeah.
Sir, I think we can take up the discussion during tea break. Thank you, Dr. Yadav, for good presentation. So now we move to the last presentation of this particular session. I invite Mr. Balaji to present his paper on curing stress effect on stabilization of low and high plastic clays in inactive and active. We have 9 minutes time.
Generative AI declaration. None of the material in this slide has been, none of the generative AI has been used. All the materials here are mine, and it's not adopted from any site. So we'll start. We'll study about the curing stress effects on stabilization of low and high plastic clays in inactive and active zone.
It's required for recording.
Oh,
You want, you can use this or that.
I'll use this. It's okay. So, I am Balaji Bandaru from IIT Madras, working under Professor Robinson and Ramesh Kannan. So, why we need to stabilize soft clays? So, soft clays are highly compressible, which means when we have stringent settlement criteria, excessive settlements are going to be observed, and it's not going to be desirable, and it will create a lot of problems. Low shear strength properties. Anticipation of higher loads. Under anticipation of higher loads, we are obviously it's not desirable. So this is a typical compression response of an untreated clay. So as you can see, the pier is going to settle substantially when the clay is existing at water content higher than liquid limit, which means it's going to compress in isotropic, normally consolidated line. So significant amount of settlement is going to happen. So we need to stabilize the soil. When we are going to stabilize the soil, induce cementation. This is what I'm going to work on. So this is a typical compression response of a cemented clay. As you can see, substantial decrease in void ratio is observed, and a substantial increase in pre-consolidation pressure, which means that at loads which desired loads which we need, we are going to observe less settlements as compared to untreated clay. So as you can see, deep soil mixing and mass soil mixing are most widely adopted applications in cement stabilization. Obviously, jet grouting is also there, but we are going to consider these effects. So the curing stress is obviously going to play a major role because when we are going to a particular depth, the effect of overburden pressure is going to play a major role on how the sample is going to cure and it's going to stabilize the soil. So we are going to study, the research gap is how the clay plasticity is going to affect the effects of curing stress response. We are going to see how the mechanism and quantitatively explain what is happening with the increasing curing stress. Later on, we'll see the positive effect. Obviously, there will be, if there is an increase, that means we can reduce the cement dosage and we can reduce the anthropogenic CO2 emissions. That's a good thing. But if there is a negative effect, then there may be certain applications where we are going to rely on, such as where we need the strength to be should not be decreasing. Then we have to check through these kind of mechanical tests. So these are the two theories which are available in the literature, commonly available in the literature. So when we are increasing the curing stress, one, your porosity is decreasing, your water content is decreasing, which means that the microstructure which we are going to observe is more compact and more dense. On top of that, we are going to have the consolidation effect, and we are going to have self-stress effect. So basically, theory 1 suggested that there is a self-stress effect and there is consolidation effect as well. These two are combined. The theory 2 suggests that there is only consolidation effect. First, we will see the problem with these two theories are postulates. They are not validated properly with the experimental results. They are just postulated based on unconfined compressive strength tests. So we are going to perform series of mechanical tests such as unconfined compressive tests, tensile strength tests, compressibility tests to check whether these theories are actually working or not. Here, under the curing stress, R is always greater than 1. Now we'll see the material. Here we are using Ennore clay. Here we are using Ennore clay to understand the effect of stabilization, to understand the effect of effect on stabilizing with cement. We are using ordinary Portland cement. We are not using any other type of cement. So these are the properties. We have considered low plastic clay and highly plastic clay. So these are the Mount Morlite sheets which are observed in low plastic clays. And now here is the clay and cement oxide composition. We also have to check whether the cement which we have taken are in the acceptable range of the acceptable range reported in the literature, which was actually in the acceptable range. And these are the oxide composition of the Ennore marine clay. Coming to the methodology and data acquisition, these are demolded for 20 minutes. Destructured. Afterwards, cement slurry at water to cement ratio of 0.6 was added, and then afterwards we pour it in the unstressed sample and we pour it there for stress sample. The stress sample was till 400 kPa. So the measurement was global LVDTs and load cell of S-beam 20 kilonewton load cell. Now, first we have to understand how this paper is going to work. So, if you want to go through this mechanism, this was published in ACTA, you can check this out. So, in my previous study, we have classified the clays, the cement stabilized clays into 4 different zones. Now, what we are going to do is, we are going to take the soil stabilized in zone 1 and soil stabilized in zone 4, and we are going to study how the effect of curing stress is going to impact the mechanical behavior in these 2 zones. And we are also going to check the behavior in highly plastic clays, which is stabilized in active zone. These zones are classified, and I will not go into detail. You can check this paper, and you can download it here. So this is the test specification which I have used. This is the inactive zone. So what is happening is, unlike what we have observed in the previous literature, increasing curing stress is not actually affecting positively until 200 kPa. After 200 kPa, there is a substantial increase in stiffness as well as there is an increase in UCS value. Inactive zone means the soil is stabilized with 5% cement dosage by weight of dry soil. In the active zone, however, the behavior is a little bit different. So when you are increasing the curing stress, just by increasing to 50 kPa, there's a marginal increase in UCS, but afterwards it's shot up once we increase to 400 kPa. There is an increase in stiffness as well. These results, although error bars are not here, these results are we have done 3 trials for each test. Now we are going to see how the variation is with 1 day sample. So as you can see before, the behavior is totally different when you are seeing the sample just cured for 1 day with the curing stress. Initially, there is a rapid increase in UCS value and the stiffness as well. This is actually the consolidation effect. Now we'll see why it's not self-stress effect. So when you are seeing this is the effect of 1 day versus 7 day response. So although we have to go through a little bit detail on why this is happening, I'm not going to discuss about it right now. We are just going to see that in certain parts there is a trend and in certain parts there is not. We need further research is needed to understand why that is happening. And this is active zone, 1 day response. As you can see, there's a totally different behavior when you're seeing in an active zone and in the active zone. There's a totally different behavior. In the active zone, there's a substantial increase in UCS value and the stiffness with increase in curing stress for 1 day sample. But when you're seeing it, when you're comparing it with 1 day versus 7 day response, that increase, although there is an increase, that increase is not carried forward with increase in curing time when your curing stress is less than 200 kPa. Now we'll see the tensile strength. The tensile strength test was carried out in, through split tensile or BTS. The sample definition, specimen size and the deformation, the strain rate are mentioned there. Now we'll see the self-stress effect. In order to see the effect of self-stress, we have to observe the tensile strength. That is an indirect measure what I'm considering in bond evolution. So as you can see, the the tensile stiffness is also increasing with increase in curing stress. But after a while, there is not much change in tensile strength when we are increasing the curing stress. So that means here self-stress effect is not actually valid. It's not valid. So which is disproving the previous theory. This is in active zone. This is active zone. In the active zone, we actually see that self-stress theory is actually not at all valid, because when initially we can attribute it, although, but afterwards, if there is a self-stress effect, which means we have to, when we are increasing the curing stress, it should actually be reflected towards the results. Now we'll see the comparison between the compressibility. In the inactive zone, which is at a lower cement dosage, the post-yield behavior is more or less similar, but the post-yield behavior in the active zone is totally different. On top of that, there is a substantial decrease in your void ratio and the compression behavior when you are checking 100 kPa and 400 kPa. But here 100 kPa and 400 kPa are identical in the post-yield behavior. Even the yield stress is not much enhanced. There is an enhancement, although I am not putting the 0 kPa here, but there is enhancement. The only point which we want to discuss is between 100 and 400 kPa, because the limited studies were conducted to see whether self-stress effect is actually happening or not. Now we finally move to the clay plasticity. Clay plasticity is also a very important point, because when you are seeing a highly plastic clays when stabilized with cement, you see that the behavior is totally different. Initially, when you are seeing till 200 kPa, there was no much increase in UCS stiffness with increasing curing stress. But here, a substantial increase. As you can see, it's more like 4-fold increase in UCS and the stiffness we have observed. This is actually a consolidation effect. We'll see why. This is also to study the clay plasticity. This is at higher cement dosage. Now here we are going to study the coupled effect. Now we are seeing the cement dosage and curing stress, how the couple is actually going to play a role. Here, when we are increasing the cement dosage, the behavior is significantly changed, because the rate at which the increase in UCS is happening with curing stress is actually decreased. Because of which what happens is, if you are going to design based on this at a dosage of this, it's going to we are going to underpredict, and we are going to have an issues in future. Now this is the BTS value. I think it's having issue. Yeah, this is the BTS. So as you see here, from 0 to 100, the self-stress effect is not valid. But however, when we are increasing from 100 to 200, here self-stress effect is actually playing a role. Critical analysis on these kind of things are necessary, which I am not going to discuss in this. So this is at higher cement dosage. As you can see, initially what I have seen is, in higher cement dosage, the behavior is totally different. Now, as you can see, 75 to 150, there is a 2-fold increase in your BTS value. There is a substantial increase in your in tensile stiffness as well. So first we will conclude this by saying why we need to understand the clay behavior in different zones, because that's where the mechanism is going to kick in. there is distinct behavior in the sample stabilized in inactive and active zone. And there is also a high effect of cement dosage on highly plastic clays with highly plastic clays. We have also seen where theory 1 is applicable and where the theory 2 is applicable. This study is going to be beneficial for site designer while designing any kind of underground for any kind of for deep mixing site. Thank you. This is IIT Madras. Do visit.
Thank you, Balaji, for very energetic and excellent presentation. Any question? Yes.
So one of the slide, I think slide number 11 also. So the rate of loading, you keep the rate of loading is something 5% per hour kind of.
Yes.
So is there any specific
ASTM.
to keep for
ASTM.
ASTM? This is specifically talking about deep mixing?
No. Actually, I'll just go to that slide. This one, right? So this is consolidation. Yeah.
Consolidation.
Yeah, this is consolidation. The consolidation here, we what we use is CRS. So it's not conventional stress-based consolidation. Here we are using strain-based consolidation because your curing stress is actually this curing time is very low. 1 day means if you are going to do a classic odometer, it may take more than it may take more than 2 to 3 days, which is not going to give us more results. So here ASTM suggests that we are going to, if it's highly over consolidated, 5% per hour strain rate is actually acceptable.
So means you refer to the ASTM.
Yeah. We can actually, there is one paper by my guide, so there we can actually calculate the strain rate through hydraulic conductivity. So using that, we can actually find the strain rate as well. Okay. Yes. So basically, that's since that is not my paper. So based on what they have said, I'll be explaining. So self-stress effect is when you're stressing the sample and the bonds between the particles is being formed. So what is happening is when you're removing that stress is no longer gone. That stress is being captured in the bond itself. So the bonds are going to have that stress. It's like the stress is captured in the bond and it's going to enhance the bond strength. So basically, if you can see here, I have not shown the effect of self-stress.
You're talking the memory of the soil?
Not memory of the soil, bond memory. Maybe we can say bond memory. It's not memory of the soil because.
That's fine. I got it. Thank you.
1 second, sir. I'd like to address it properly. No, this is not. No. So the thing is here, as you can see, the bonds between the particles are more or less constant. So what the theory suggested that these bonds are going to be more, there will be enhanced bond formation. So that is what they suggested. So that we can actually check through direct tension or tensile strength, which indirect tension. So that is what I have checked.
Good. Thank you.
Okay.
Okay, so with this, we are coming to end of this particular session. So in this session, we had one theme lecture by Dr. Sita Lakshmi and followed by 5 contributor presentations. So all the presentations were very, very good. Researchers used, different materials from xanthan gum, cement, bentonite, biochar, then geopolymerization. So many variety of materials were used for stabilization. So couple of common things in all the research is soil responded very well. If you had anything and everything, all materials soil responded very well. And also the second bottom line was the cost effectiveness. Okay, so all the driving through the cost effectiveness, the cost effective ground improvement was apparent and visible from all your presentation. I really appreciate that. And I would like to basically thank all the authors for excellent presentation And special thanks to all the audience for, highly, interactive session and asking a very, very good questions. So with this, we conclude this particular session, and I hand over this session to our moderator, Dr. Yadav, for, further moderation. Thank you.
Thank you, sir. I would like to invite Amarnath sir for handing over this particular moment to our theme speaker. Now I would like to present certificate of appreciation to our chair, Professor Amarnath. Please come, sir. Now we can close the session. Thank you everyone for attending the session.